Hello. Before you is the last example of axial stretching and compressing in a statically indeterminate system. Example 3. Welcome. A beam hinged and anchored by two rods is loaded with a continuous load. Based on the strength condition, calculate the diameter of the rods. Given A1 equals A2, E1 equals 2 times E2, tensile strength 60 megapascals, compressive strength 90 megapascals. The beam is hinged and anchored by two rods, loaded with a continuous load. Let's mark the reactions at the support and the forces in the rods. We have reactions at the non-rolling support. Two reactions, a horizontal component and a vertical component. We have forces N1 and N2 along the axes of the rods. So we have 4 unknown reactions. In this task, we can use 3 static equilibrium equations since the sum of the projections on the x-axis and y-axis will give us some relationship. Because the forces are at an angle, we have them in both directions. And the sum of moments will give us some relationship. But we have 3 equations and 4 unknowns, which means the task is statically indeterminate. We need a geometric condition. Now, when we sum the projections on the x-axis and the y-axis, in those equations there will be either RAY or Rx. And they aren't really of interest to us in this task because we are interested in the diameters of the rods, so we need the forces in the rods for the strength condition. So if we take the sum of moments about point A, we will get a relationship between N1 and N2. And if we establish a geometric condition, we will get a second relationship between N1. So we do not need to sum projections on the x-axis or the y-axis in this task, because we are interested in the reactions in the rods. Of course, these sums of projections would give us some dependencies, but there would also be the reactions Rax and Ray, which we do not need. So here the geometric condition is crucial. We will take the sum of moments about point A equal to 0. Now, it is more convenient in this task. Generally, I believe that it is worth decomposing forces that are at an angle into components. As I mentioned in previous examples or videos, if we denote angle alpha here, we have force N2, the reaction in rod N2. Here is some angle alpha. The component at which this angle is, the x component is times cosine of this angle, and the other component is times sine of this angle. This is an ironclad principle that is worth applying, so you don't have to think too much. So here will be force N2 times cosine of angle alpha, and here will be force N2 times sine of angle alpha, and we can determine cosine and sine of angle alpha because we have a length of 4 here and a length of 3 here. So from the right triangle there is no problem. So I take the positive moments to the right, and like this, N1 times 2 to the right on arm 2 minus N, and now I haven't mentioned yet, we can shift the force N2 here to the point of attachment with the beam. We can do that, and then its direction of action, this horizontal component, N2 times cosine alpha, passes through the pole of the moment, meaning this component doesn't act on any arm, so it doesn't produce a moment. Then only this vertical component N2 times sine alpha acts over the whole arm of 6 meters. And so we are considering it, and it rotates negatively. So minus N2 times sine alpha, vertical component, times 6 meters, and add the continuous load, that is, the load value times the length of the beam on which this load lies. That is 8 times 4, and times the distance from the center of mass to the pole of the moment. The center of mass is in the middle, so here is the resultant of this continuous load, and this distance is 4 meters, so 8 times 4 times 4. Rotates to the right equals 0. From this, we can determine N1, that is, the rest to the right side, divide by 2. And also sine alpha, cosine alpha, alpha is here, so sin alpha is 3 to 5. Where do we get that it is 5? Well, it is a Pythagorean triangle. The legs 3, 4, so the hypotenuse is 5. So 3 to 5 is the sine of this angle, and 4 to 5 is the cosine of this angle. So we substitute sine 0.6, and we have n1 expressed in terms of n2, and the geometric condition. Now we need to consider what happens in this system loaded with this continuous load. This is a fixed support, but it can rotate, the beam can rotate. Certainly this continuous load will stretch the second rod. That is logical, and it will compress the first rod. Nothing else can happen. And there will be a rotation. Well, since the continuous load is lying here, it will cause some rotation of this beam, like to the right. And what do we need to mark on this drawing? We need to mark that there will be a shortening of the first rod, delta L1. There will be an elongation of the second rod, delta L2. Mark the permissible displacement line of the second rod, that is, in the direction perpendicular to the elongation. We must assume that for such small angles, because these displacements here are small, so this angle is, you could say, minimal, small, very small. So for such small angles that we are considering, we need to make certain assumptions. Well, how would this beam rotate? Well, this beam on such a radius, the length of the beam would be the radius of rotation. In reality, it would want to rotate somehow, not in a straight line as I marked here, because then it would have to elongate. And we assume that it doesn't elongate, it just wants to rotate. So in reality, with larger angles, it would trace a rotation here on some radius. But for the small angles we are considering, we assume that the first phase of this displacement occurs in a direction perpendicular to the end of the beam. That is, in a direction perpendicular to the beam is the displacement of the beam's end. And now that we know all of this, we can already see this geometric condition, of course, from this triangle that has formed here and from this. Here, the condition is similar to the previous task. If we assume that delta L1 is FB, or any other notation, and let this length be FA, then FB to 2 meters is like FA to 6 meters. From this triangle, I have also transferred this angle alpha here. Here we have a half right angle, here is alpha, here is a right angle, meaning angle alpha plus this angle together form a right angle. So here is a complement to alpha. Thus, in this right triangle at this point must be angle alpha. So delta L2 to FA is the sine of angle alpha, which implies that FA2 equals delta L2 over sine alpha. FB is simply delta L1, so we substitute this FA and FB into this relationship, rearranging, and we have 6 times sine alpha times delta L1 equals 2 times delta L2. We remember the formula for elongation of a rod, n times L divided by E times A, and we substitute sine alpha equal to 0.6 comma, and here is a very important point. As we established from the problem's conditions, there will be a shortening of the first rod, so delta L1 is negative. Because there will also be a shortening, so the force in this rod, meaning N1, must be negative, which is why this minus sign appears here, and it is, well, crucial, you could say. If we do not take this minus into account, the rest will be wrong, so this is very important. We can already write here that this is minus FB. We simply need to remember that this delta L1 is negative, meaning the force in the rod is negative minus N1. We substitute the rest, multiplying these numbers here, 2 times 5, here multiplying the numerators. From the problem statement, E1 equals 2 times E2. I substituted, and now we multiply by the part of the denominator E2 times A2. Canceling out, dividing by minus 5 and 40, we find that N1 equals minus 1.85 times N2. Moving this to the next slide. And also from the sum of moments, we have this relationship. From the geometric condition, we have this relationship. Here is this value n1. We substitute it up and calculate from this n2. n2 equals 17.53 kn, because everything was written in kn. We substitute into the first or second equation and calculate n1 equals minus 32.43 kn. Now the strength condition is as follows. The first rod, compressive strength, the second rod, tensile strength, compressive strength is 90 megapascals, tensile strength is 80 megapascals, meaning the absolute value of the force in the rod divided by the cross-sectional area must be less than or equal to the respective strength. Thus, the stress in the first rod, the absolute value of n1 divided by the cross-sectional area, here times 10 to the power of 3 because it is kilonewtons, must be less than or equal to 90 megapascals, meaning the compressive strength, because the first rod is being compressed, right? I immediately wrote down the second condition. Stress in the second rod, which is the absolute value of the force in the rod divided by the cross-sectional area and the tensile strength. From the first condition, the area A would be 3.6 times 10 to the power of minus 4. And from the second condition, 2.92, we take the common part, which is the larger area, which is this one. And we had to dimension the diameter, so I assumed this area to be a bit larger. From the condition, it turned out that it should be greater than or equal to 3.60, let's assume an area equal to 3.65 times 10 to the power of minus 4 square meters for the area. We remember that it's safer if the area is greater, then smaller stresses and extensions occur, but we also don't want to over-dimension this cross-section. So nothing will happen if we round to 3.65 times 10 to the power of minus 4. We have a circular cross-section. The area is pi times d squared divided by 4. That's the formula for the area. We equate these values, multiply by 4 over pi, and take the square root, and we find that the diameter should equal 2.15 centimeters. The result on the calculator at first gives us this in basic units, meaning in meters. We can convert it to centimeters. And that's all. If you have any doubts about the problems being solved, I encourage you to ask questions under the video. I will definitely respond to each of them. I recommend our other productions. I encourage you to subscribe to the channel, then you will be up to date with new materials from EduPanda, which will be increasing. Thank you for your attention. Best regards. Goodbye.